Let's start chapter 8.1, which is about sequences. A sequence is a list of numbers in an order. Here's the first number, here's the second number, here's the third number, here's the fourth number, etc. So I have some example sequences written here. I've tried to choose some that are particularly nice. How would you describe this sequence? You might recognize those as the perfect squares, right? Like 9 is 3 squared, 16 is 4 squared. So we could say these are the perfect squares. How about this sequence? 1, 2, 4, 8, 16, 32, 64, 128. Those are powers of 2. This one's a little trickier. 1, 1, 2, 3, 5, 8, 13, 21, etc. Maybe you've seen that before. That's called the Fibonacci sequence. And how do you get that? Well, if you add the 2 and the 3, you get the 5. If you add the 3 and the 5, you get the 8. If you add the 5 and the 8, you get the 13, etc. Here's a bunch that you probably haven't seen before, and that's okay. If you wanted to write a square wave as a sum of sine waves, you could do 4 times sine 1x plus 0 times sine 2x plus 4/3 times sine 3x plus 0 times sine 4x plus 4/5 times sine 5x, etc. And eventually, after adding up infinitely many terms, you would get a square wave. Before you got to infinity, you would get an approximate square wave. If you did the same thing with these coefficients, you would get a triangle wave. If you did the same thing with these coefficients, you would get a sawtooth wave. But these are also the coefficients for the Taylor series for log x at c equals 1, so that's an interesting coincidence. How about these numbers? Can you see any pattern here? 1, 1, 2, and then 6 is 3 times 2, 24 is 4 times 3 times 2 times 1, 120 is 5 times 4 times 3 times 2 times 1, so this would just be 1 over n factorial. So generally, if we want to refer just into a sequence in the abstract, we would say a sub 1, a sub 2, a sub 3, a sub 4, ... And you might say a sub n out there is the nth term. This is actually a function of n, just like f of x is a function of x, but n has to be an integer here and rather than any fractional number. So you can kind of think of these as functions. They are functions. So it's a function of n, which means we could write it as a function. A sub n like that, or a of n like f of x. Why don't we just use f if these are a function? Well, later we'll want to be comparing these sequences to ordinary formula-based functions like x squared and 1 over x cubed and stuff. So it's nice to have a distinction in our notation between sequence type functions and continuous type functions. So we'll generally write them with subscripts, but if you're dealing with Wolfram alpha, which is handy for a lot of this stuff, it likes to write them as a of n rather than a sub n. And then another question that we'll be dealing with, I said starting at the first term, like this is the first term, that's the second term, right? But then the 2 is here. Maybe it would make more sense to call that the 0th term. Even some programming languages, some of them start at the 0th element of the array, some will start at the first element of the array. So we're going to do what our textbook does and default to starting at n equals 1. Not n equals 0, unless someone specifies something else, like in this sequence we start at 0, or in this sequence we start at 2, or something. So we're defaulting to starting at n equals 1, not n equals 0, until we get to one particular kind of series or sequence, and then we'll start defaulting to 0. So I'll mention that when we come up against it. All right, so there's a few sequences, and a lot of the fun of sequences is, given a set of numbers, come up with a formula based on n that gives you that sequence of numbers. So we'll talk about that next.